So thank you, Wes. Again, I'm Sergio Ammirata. I'm the chief scientist at SipRadius and also the maintainer of the libRIST open source project. And today we'll be talking about how RIST can support end-to-end live streaming in a broadcast scenario, meaning streaming to as many users as your bandwidth can support, the typical one-to-many broadcast scenario. So there's two important keywords that we're going to mention all throughout the talk: IPMX and RIST. Right? We're going to assume you're familiar with these terms, but just in case, here's a one phrase summary of what each of these means. IPMX, a set of open standards for transporting audio, video, and data, and the IPMX focus on control, copy, protection, and security. And RIST is a transport protocol based on UDP that includes packet recovery and security. So we're going to be discussing the two topics separately. First, we'll talk about how IPMX comes into play in this context, and then we will do a deep dive into the use case that we're mentioning of streaming to thousands using RIST. So let's start with the IPMX first. Okay, here's a problem we face. The IPMX standard for our particular use case has not been written, right? So what do we do? Okay, hold on, sorry about that. So we have to assume what the other specs assume. What does the IPMX wants to achieve? It wants to transmit all the data across the link. We don't want to chop any other pieces. We want audio, video, and all the metadata. We want to make sure the link is protected with some sort of encryption and or authentication. We want to make sure it has copy protection, DRM, HDCP, some form of fingerprinting in the case of audio video. And we want to make sure it has proper timing, that whatever clock we have at the source makes it to the destination at playback, so that everything plays back accurately, including the metadata. All right, so how do we achieve these goals? So first goal, transmit all the data across the link without losing any pieces. So we're going to leverage RIST ability to pass binary data from end to end. So we don't have to touch the binary data. We can send all of it. How do we ensure the link is protected? We leverage RIST encryption and authentication for copy protection. We don't touch the original payload when we do so we can do a pass-through DRM. And lastly, for the clock issue, we use MPEG-TS. Okay, now we're going to go to the live streaming end-to-end. Now that we know what the goals are for IPMX, we can go to the next use case. And we're going to describe with a diagram the project that we worked on. Okay, we're going to show here the live streaming workflow. We have three major blocks: the sources, the sender, and the receiver. They're the squares. And this bottom part represents the thousands of receivers that are going to want to receive the stream, and the block is here. So the sender can be FFmpeg, VLC, OBS, or a commercial encoder of some kind. Then it's going to basically start sending data as MPEG-TS to our sender. And sender, using the RIST protocol, is going to fill the buffer. And as soon as it fills the buffer, it's going to start an output port listening to the communication. So next, we have the handshake, right? You send the buffer, and we're going to start a handshake exchange. This is an oversimplification of the EAP SRP68 protocol. It's a lot more complex than this, but for the interest of our presentation, it gives you an idea what's happening. There's a full spec that we have published. So the receiver starts the handshake process. The sender sends back, yes, I hear you. The username is found, and then it asks for the password hash. Then the password hash is exchanged, and now the receiver has been authenticated, right? Now that the receiver has been authenticated, the sender is going to transmit the key, the encryption key, And then the communication can start over an encrypted channel. So we have authentication and encryption. So we just described the process for live streaming and low latency, right? We can achieve 300 milliseconds glass to glass. We have already done this all over the US for a major broadcaster. When you expand this with a borderline quality, or when you use this with where you have borderline quality or intercontinental links, you're gonna have to increase your buffers, and then you're gonna reach the higher latency, but overall we get under 1 second regardless of where you are, and regardless where the sources are as well. And because this is UDP based, unlike HLS or Dash, you will never get the spinning wheel buffering, right? Even with a low latency HLS, you cannot achieve this level of reliability unless you use a protocol like this one, where the end-to-end is transmitted with UDP-based protocol, with RIST on it for packet recovery, with full-blown authentication and encryption, and where each one of the receivers is authenticated separately with a username and password. So let's move to the specific tools we use, right? The library includes a utility called RIST to RIST. And that utility is what allows us to do this. It acts as a transparent relay, right? It can live in a central cloud with a public IP where the sources and all the destinations can connect. It supports listener mode, so you can start it and it can be listening to any device that wants to connect and receive the stream. It has full-blown authentication, so it can act as a gatekeeper to all the connecting clients. And it doesn't have any latency introduced by the tool because it doesn't demux, remux, it doesn't do anything except grab the binary data and transmit it all over the place. So you can see how with this tool, you can create your own CDN and you can scale up, okay? So let's talk about scalability. How does this scale up? You have, from our experience, the sweet spot for this type of stream when we deployed it was either 720p or 1080p at 3 to 5 megabits, which basically allows you to traverse any firewall, VPN in a corporate environment. We recommend not loading the RIST-to-RIST utility, which is part of the libRIST package, to anything more than 100 simultaneous connections. And the way you achieve scalability is then you start more instances of the same application on the same machine, or you do sideways scalability and then you do multiple machines and you split the load that way. So the utility for managing tons and tons of uses has an optional file that where you could create users and password with an Apache-like authentication file format. For those of you that have done basic authentication in Apache, there's an HT password utility. We provide a utility very similar called RIST SRP password. You call the utility with the username and password. It gives you a hashed line, and you just pipe that hash line into a file. And then when you start the RIST to RIST or the RIST sender, you go ahead and like we show here, you pass the file as part of the startup command line. So now all the authentication for all the connecting devices is going to go and look at this file. And this authentication protocol, the SRP, never exchanges the password on the clear. So it doesn't require an encrypted communication to begin with. It's part of what makes this very secure. All right, for the last part, let's talk about the receivers themselves, right? In our case, we use a slightly modified version of VLC 3.0. We grabbed VLC 3.0 and patched it with the libRIST library input support. And then we use that as a player inside a Raspberry Pi, in our case. The beginning secret between the encoders or the sources and our RIST relay, you want to transmit that, whatever method you want to transmit is a one-time thing. But then for the client, for the playback, it's better if you have it present a username and password like you do when you log into a site. You don't have to exchange it. Somehow they have their credentials, and now they can view any stream just by presenting the username and password. The last thing that needs to happen when you use RIST, which is important, the sender and receiver parameters, they have to match your buffer size, your packet reordering buffer, etc. And if you use libRIST, those parameters are passed automatically between sender and receiver, so you don't have that burden if you have at least the open source libRIST implementation. So in our case, we have this running we have about 900 streams running as sources. We have over 3,000 STVs playing those sources, and it's all being done just with a handful of VMs acting as relays. About 8 VMs is all we need. We did scalability by doing what we call RIST on demand. The connection to the sources is only open when somebody requests the signal. So that's why we're able to have 900 streams, and yet only manage everything with 8 virtual machines. So we can summarize the aspect of presentations in 2 things. IPMX side, we think that the solution is in line with the IPMX philosophy. Perhaps when they write the spec for this type of end-to-end, it will match, or it will be using open standards like we did here, and we take care of all the parts, especially the clock, transferring the clock from the source. It could be even a PTP clock. Once we put it in the MPEG transfer stream, we have the clock embedded. We no longer need PTP. We go all the way through with our clock to the very end with accurate synchronization, with a protocol that has been running for 20 years, no problem. And the rest is using the features that are already built in and proven in the RIST protocol. In this particular case, we use the libRIST library and all the tools that comes with it. So, thank you very much.